A very good morning and welcome back to the course of microwave engineering. So today we will continue with the microwave measurement module. If you recall, in our previous lecture, we have seen a procedure to measure the unknown microwave frequency without using frequency meter or wave meter. And in the previous lecture, we have also seen a procedural method in order to measure the given complex load of impedance. Okay, so in today's lecture, we will start with the measurement procedure of the microwave power, and then after that we will continue to a procedure to measure the different types of losses that will get encountered in the microwave signal processing. So today we will devote our lecture in order to understand the measurement of microwave power and the measurement of different types of losses using the same approach, the setup which we used as a low cost laboratory, in which we are going to make use of a low frequency signal to modulate the microwave source. And typical microwave source, we are going to make use of a klystron, reflect klystron, and that signal we are using it as a microwave signal, right? So here again, in the procedure of power measurement, we are going to make use of that laboratory technique. So let us start with microwave power measurement. So I will start from here. Microwave power measurement. Before the measurement procedure, you should know the basic fundamentals of a power quantity. Okay, how the power is represented, okay, and the terminologies associated with the power, right? So how the power is defined. So the definition of power, I will write over here. Definition of power. So how the power quantity, power is an electrical quantity, right? So microwaves can be measured for their power. So the power is defined as the quantity of energy, right? It is a quantity of energy dissipated or stored per unit time. Okay, so a simple definition of any power it can be given as the quantity of energy which is dissipated per unit time, or the quantity of energy which is stored per unit time, right? So here the quantity of the power, quantity of energy when it get dissipated, so this particular indicate resistive network when the dissipation happens. Okay, so when the energy gets dissipated, the dissipation is indicated by resistive circuit, while if the energy is getting stored per unit time, then this particular phenomena is indicative of reactance, right? So whenever the energy is getting stored, the energy is getting stored in the form of a reactance. And again, there will be two different types of energy storing capacities. One is inductive and another is a capacitive, right? So inductive and capacitive reactances, when used, they have the ability to store the energy, and hence they can be considered as a power storing element. Okay, so the special example in the case of the tank circuit or the resonant circuit or the oscillator circuit, we are going to make use of a reactances. So reactance has the ability to store the energy per unit cycle or per unit time. So that means the inductor and capacitor do have a property to possess or to hold the energy, and that's why they can become a source of a power, right? On the other hand, if we make use of a resistive circuit, the energy in the resistive circuit will dissipate, and this main dissipation is in the form of heat production, right? And here we are not going to store any particular energy, but the energy will get dissipated in the form of a heat, and that particular circuit or network is being characterized as a resistive network, right? So we go ahead and we saw the definition of what do we mean by a power. So the microwave power is basically categorized distinctly into three types. So microwave power category, it is distinctly divided into three different categories. So first category is, we call it as a low microwave power or low power. So whenever we say a low microwave power, we say less than 10 milliwatt. Less than 10 milliwatt. Right? The next category to the lower power is a medium power. The second category of microwave power, we call it as a medium power. Now in medium power, the power handling capability will be between 10 milliwatt to around 10 watt, right? And the third category of microwave power, we can call it as a high power. So the high microwave power, which is normally characterized as the value of power greater than 10 watt. Greater than 10 watt. So any particular microwave device, if it is generating the microwave power in this particular range, accordingly it can be classified. Okay, so the device which we use at the laboratory in order to produce the microwave signal, it is normally classified as a low power device. Okay, so for example, if we make use of tube based device, the best example in the laboratory, we are going to make use of a reflect piston, right? So it is a low power device. And similarly, if we take the example of semiconductors, then impart and the gun diodes, they also have the low power operation. So normally wherever we are going to generate a microwave signal in the laboratory based setup, that power of the microwave is categorized as a lower power, okay, which is less than 10 milliwatt. We go ahead, and how the average power is measured in the circuit. So the average power measured by calculating the integration 1 upon n into t, integration from 0 to nt. Okay, so the product of voltage and current dt. Okay, so this is a simple equation with which we can evaluate the power, where t is the time period of the microwave signal, okay, and n is the number of cycles, right? Okay, so on the other hand, if the microwave power operation is considered to be peak power, then the same equation will get modified to peak power operation, power peak. So how it is given? It is given as 1 upon tau, integration from 0 to tau v of t I of t dt. Okay, where the relationship between the average power and peak power operation is given as the average power is always equal to peak power multiplied by duty cycle, right? So this duty cycle we can replace with the tau, which is the pulse period. So tau is a pulse period or pulse width, we can say. So this peak power multiplied by the duty cycle we can write tau multiplied by PRF, where this tau is the pulse width, tau is the pulse width, or we can also call it as a pulse duration. And PRF is a pulse repetition frequency. Pulse repetition frequency. Okay. So this pulse repetition frequency and the peak power consideration is only considered during the pulsed operation of the microwave device. Okay. On the other hand, we normally make use of power quantity in the form of an average value, right? So peak power is considered whenever we consider the pulsed operation of the microwave signal. Okay. On the other hand, in the continuous processing of the microwave signal, we will normally consider the average power, right? So the relationship how to measure the power in the normal scale, that is in the linear scale, and in the decibel scale, that is expressed in terms of dB milli configuration. Okay, so here the power in dB milli, so it is written as dBm. It is a popular choice to make use of this particular unit in order to measure the power. So power in dB milli means dBm, that means the decibel compared over 1 milliwatt, right? So the equation is 10 log to the base 10. Okay, so first of all you need to take power in watts. Whatever power we measure, that we take in watts, we divide that power by 1 milliwatt. Okay, we take this ratio and we take the logarithm scale. Okay, so when we take this logarithm scale, the power in the watt will get converted into decibel milliwatt. Okay, so that means if we take 1 watt over here, 1 watt power, so this 1 watt power in terms of dBm, how it can be written? Power in dBm is equal to 10 log to the base 10. Now power in watts is 1 watt. 1 watt divided by 1 milliwatt means 10 raised to minus 3 watt. Okay, so this can be written as 10 log to the base 10, 10 raised to 3, right? Okay, so this can be written as a 30 log of 10, and this is nothing but 30 dBm, right? So that means if we take the power as a 1 watt, the dB milli scale for the 1 watt power will be 30 dBm. Okay. On the other hand, if we take 1 microwatt power, 1 microwatt, or that is nothing but 10 raised to minus 6 watt. Okay. So this case, how the dBm power is then given? dBm power is given by 10 log to the base 10. So power in watts is 10 raised to minus 6 divided by 10 raised to minus 3, 1 milliwatt. Okay, so this can be written as 10 log to the base 10 of 10 raised to minus 3, right? And this can be written as minus 30 log 10, right? And this can be written as minus 30 dBm. So here please remember 1 watt corresponds to 30 dBm, and when we take 1 microwatt, it corresponds to minus 30 dBm, right? So this is the conversion process from watts into dBm, right? So let us now measure the process in which we can quantify the amount of a power. Now let us say how we can measure the microwave power. Okay, so the microwave power can be measured in a different ways. So here I will list out the ways to measure the microwave power. Ways to measure microwave power. Okay, so this can be classified into two categories. How to measure the microwave power? By using costly devices. This is one technique, and This particular technique sometimes also called as a direct method. And there is another way. Whenever we don't have costly equipment to measure the power, we can go ahead with low cost method. Now this low cost method is normally laboratory based. Okay. So the first method, which makes utilization of a very costlier equipment, for example power meter with power sensors. Power meter with power sensor. Okay. And when we go with the low cost method, we can make use of Bolometer circuit. Okay. Thermocouples we can make use of. Okay. So Bolometer and thermocouple, these are the choices to measure the microwave power at low value, low power. Okay. And if we want to measure high power, then we are going to make use of calorimeter and wattmeter. Okay. So these instruments we are going to make use for the measurement of medium and high power. Say whatever the method of measurement of the microwave power, the principle is same for all these methods. Whether the method is a direct method, which makes use of sophisticated equipment like power meter with the advanced power sensor, or the method which implements low cost laboratory based equipment, reflectoston tube, and the other low frequency circuits like bolometer, thermocouple, calorimeter and wattmeter. So in all these techniques, the principle of measurement of the power remains same. How the power is measured? The principle of measurement of power, here I will elaborate you. The principle of measurement of power measurement. So this principle is applicable for all these techniques and different methods. Okay. So what is the principle behind the measurement of power? So the principle is the power is allowed to generate heat. Yes, the power is allowed to generate heat. So whenever power is allowed to dissipate in the resistive circuit, then it will generate a heat. So that means here we are going to make use of resistive circuit. Using a resistive circuit, because we know that whenever the power gets dissipated in the resistive circuit, it will generate a heat. Okay. Now this generated heat is then measured. This generated heat is then measured by temperature sensing equipment, or you can say temperature sensor. Okay. Now this temperature sensor device will establish a change in the electrical parameter. So this temperature sensor will cause change in current or voltage, and this corresponding change in the current or change in the voltage will corresponds to the appropriate amount of generated power. So this is the simple basic fundamental how the microwave power is measured, and this particular principle is applicable for all these methods, whether you are making use of direct costlier equipment or you are going to make use of low cost standard laboratory based setup, right? So the principle of power measurement remains same. So what is happening? So how to measure the power? The power which you want to measure is allowed to dissipate in the resistive network. when the power gets dissipated in the resistive network, it will generate heat, right? Now that generated heat is conveniently measured by using certain temperature sensor. Okay, so in the costlier equipment, the temperature sensor, directly we are making use of a power sensor. But in the cost effective method, in the low cost technique, we are going to make use of variety of different circuits like bolometer device, thermocouple, thermistors. Okay, we can make use of a calorimeter and wattmeter in order to measure that heat produced. Okay, and that heat produced is then again converted into electrical quantity, and there will be variation in the voltage or current as a representative. Okay, so this variation in the electrical quantity proportional to the heat generated is the direct indicative of power measurement. Okay, so one such a setup in order to measure the low power microwave that I will show to you. Okay, so this particular construction of low power measurement of the microwave, we call it as a bolometer technique. So what we do in this method, so here I will draw that. So we are going to make use of a bridge arrangement in which one of the arm will contain the temperature sensor device. So this is a popular bridge circuit, you already know. Okay, and at the center of this bridge circuit we will place a sensitive galvanometer. Okay, and here in the one of the arm of this bridge circuit we will place temperature sensor, right? Now this temperature sensor, you can make use of a thermocouple or you can make use of the thermistor. The thermistor again could be of two different types, positive temperature coefficient or it could be negative temperature coefficient. So place that temperature sensor in one of the arm of the bridge circuit, right? So let us say these are the resistors R1, R2, R3 and R4, where R4 is the temperature sensing device. Okay, and this bridge we are going to connect to a constant current supply source in this way. So let us say this is resistance 4 and let us say here we will place one more resistor in the parallel R5. Okay, and this we will put like this, variable resistor we will make, and we will place a series milliammeter in the circuit. Okay, and then we will place a DC source in this way. So this is a typical construction of bolometer device. Okay, so this is a typical construction of bolometer type of power measurement. I will write here bolometer type of power measurement. Now this particular setup is especially used in order to measure low power microwave signal, right? So here the temperature sensor is placed in one of the arm of the bridge circuit. So this is the bridge circuit. You can also call it the Wheatstone bridge also, right? Now initially, before applying the microwave signal, so remember over here the temperature sensor is exposed with a microwave signal in this way. So the microwaves are being radiated over this device. Okay, so when this microwave signal gets incident on this thermal sensor, right? So this thermal temperature sensor, we can either make use of a thermistor or thermocouple in one of the arm of this bridge circuit, and whenever the microwave signal is incident on this particular temperature sensor device, the temperature of this particular device will change, and when the temperature gets changed, the bridge will become unbalanced. The bridge will become unbalanced, and whenever the bridge will become unbalanced, we will see the deflection in the current. Okay, so initially when the microwave signal is not applied, the bridge is going to remain balanced with the help of this DC voltage and the current supply, right? So whenever the microwaves are led to incident on the thermal sensor, the resistance of that thermal sensor will change and the bridge circuit will become unbalanced, and because of unbalancing we will get deflection in the milliammeter. Now this deflection or the change in the current, we call it as a change in the current, delta I. So this change in the current this is produced by unbalanced bridge condition. And when the bridge will get unbalanced, the bridge will get unbalanced whenever the resistance of the temperature sensor in one of the arm will change. And why the resistance will change? The resistance of that temperature sensor will change because of the incident microwave power or microwave signal. So it will unbalance the bridge. Whenever the bridge will get unbalanced, we will see the current flow in the milliammeter. Now this change in the current flow in the milliammeter, it is directly proportional to, so this delta I is proportional to the power sensed by thermal sensor, right? So this particular mechanism or circuit, in order to measure the low power microwave signal, we call it as a bolometer type of power measurement technique. Okay, so this entire arrangement we call it as a power measurement technique for the low power using bolometer circuit. So this entire circuit we call it as a bolometer type of power measurement, right? So in the case of high power measurement and medium power measurement, we use the sophisticated devices like wattmeter and calorimeter, and in that particular case the high power measurement is again can be carried out by measuring the proportional heat produced, and that proportional heat produced will be automatically converted into electrical parameter, and the change in the electrical parameter corresponds to the generated amount of power. Okay, so this is the simple principle of how to measure the microwave power. We saw the definition of microwave power. We saw the different types of microwave power in the peak operation and in the average operation. We saw how to convert the power into dB scale and into watt scale. Okay, and then we saw the different methods to implement the power measurement system. Okay, and we saw a typical measurement procedure of low power of the microwave signal using a bolometer technique. Okay, so I hope you understood what is the basic principle of microwave power measurement. Okay, so now what we do is we go ahead and we will see the measurement of different losses of the microwave signal. So the next discussion I will write over here, measurement of, I will choose a different color before, measurement of losses. I will give the heading as measurement of losses. Now what different types of losses will be encountered in the microwave operation? The different types of losses that we encounter normally during the microwave operation is attenuation loss, that is the signal loss. Okay, then we have the reflection loss because of the reflected waves. The reflection loss is also known as return loss, right? And third type of loss is because of the insertion of the device itself. We call it as the insertion loss, right? So we already know the relationship between all these three different types of losses. So the relationship is insertion loss is always equal to, so here I will denote insertion loss is always equal to reflection loss plus attenuation loss, right? So this is the equation which relates all the different types of losses with each other. So when return loss is 0, when return loss or reflection loss is 0, then at that time insertion loss is going to become equal to attenuation loss, provided if there is a no reflection or return loss. And under what situation the reflection or the return loss becomes 0? When the circuit is perfectly matched, there will not be any reflected wave, and in that particular case reflection loss will be 0, and the insertion loss of the circuit will only contributed because of the attenuation, right? Now let us say if we have input power denoted by Pi, let us say Pi is the input power, okay, and let us say PR is a reflected power. So this power is indicated a microwave power, please remember, okay. So here whenever, let us say this is a network, a 2-port network having port 1 at the input and port 2 at the output. This is an output port and this is an input port. If Pi is the incident power, okay, and PR is the reflected power, okay, then actual amount of power that enters into the network is nothing but Pi minus PR, because PR is the reflected power and the reflection will take place at the input port itself. Therefore, the actual power that will get delivered to the network is the simple subtraction of input power minus the reflected power, okay. So here the input power which enters into the network is Pi minus PR. So this power will actually input to the network, and this power when gets propagated through the circuit, there will happen the attenuation loss, right? So therefore whatever output signal we get over here, let us say PO is the output power that we are supposed to get at the port number 2 output port, okay. So this output power is always less than the input power because of all these reflection losses and the attenuation losses. Therefore the insertion loss is defined as the difference in the power arriving at the terminating load with and without network in the circuit. So if we take the ratio of output power PO to the input power, so this can be represented as Pi minus PR divided by Pi multiplied by PO divided by Pi minus PR, right? So here the same equation is going to become true. Insertion loss is equal to reflection loss plus attenuation loss, right? So how this can be written then? So if we take the log on the both side, okay, so if we take the log on the both side of this particular power equation, I can write 10 log to the base 10 of the ratio PO divided by Pi, right? So this can be written as 10 log to the base 10, okay. So first of all I will write Pi minus PR upon Pi input power, okay, and because of the logarithm we took, we will change the multiplication into addition. 10 log to the base 10 PO upon Pi minus PR, okay. Now this can be simplified further, so this can be written as 10 log to the base 10 on the left hand side, output power divided by input power Now this can be simplified as 10 log to the base 10 of, okay, so this can be written as 1 minus PR upon PI. We can write in this way, okay, and this will remain as it is 10 log to the base 10 of PO divided by PI minus PR. Okay, so here the insertion loss is on the left hand side. So the insertion loss is denoted by IL, right, and it is given by left hand side 10 log to the base 10 of P0 divided by PI. So if we take the ratio of output power divided by input, and if you take the logarithm, we will get the insertion loss in dB. Similarly, the reflection loss, I will write reflection loss is sometimes also called as a return loss. Okay, how it is given? It is given as on the right hand side 10 log to the base 10 of 1 minus PR upon PI in dB. Okay, and similarly the attenuation loss, right? So the attenuation loss, how it is calculated? Attenuation loss A is equal to 10 log to the base 10 of, okay, P0 divided by PI minus PR in dB. Okay, now here we want to measure these powers. Okay, so we will see a measurement procedure in which all these powers for the losses can be calculated. Okay, so we will see a measurement technique of all these losses by using a setup. Okay, so here we have microwave source. So here this is a microwave source. Okay, now this microwave source is connected to the further circuit using the isolator. Okay, so this is the standard setup of measurement. Then we are going to make use of frequency meter in order to measure the frequency of the generated microwave signal. Frequency meter. Okay, now this frequency meter, after that we will place a variable attenuator. Okay, we will place a variable attenuator. So here we have variable attenuator. Okay, now this variable attenuator we are going to connect further to directional couplers. Okay, so this is directional coupler 1, right here, directional coupler 1. So this is, I am drawing the setup in order to measure all these losses, right? So we will have another directional coupler, directional coupler 2. So this is also a directional coupler, second one. And then we have the device for which we want to measure these losses. So the device under test will be kept over here. Okay, and here we will place a detector probe of the test bench. Detector probe. Using slotted waveguide section also we can make use of, and here we will place a termination. Okay, so this termination is a match termination. Okay, and in the directional coupler also we are going to place over here two separate detector circuit. Okay, so here we will place a detector, another detector probe, and for the second directional coupler also we will place another detector probe. So we are using 3 detector probes. Okay, and here the second detector probe we will terminate into a termination, suitable termination. So here we will place a termination. Okay, and the first detector probe we will connect to output device. So here the output device is a CRO or VSWR meter. Okay, so I will connect all these blocks now. Now the source is connected first to the isolator. From the isolator it is connected to the frequency meter. From the frequency meter the signal is attenuated variably. Okay, and then it is given to the directional coupler. Okay, now from the directional coupler it is given to the second directional coupler. The another part of the directional coupler is connected to the detector probe number 1. Okay, and the detector probe number 1 is connected to the output device, whether we can make use of a CRO or we can make use of a VSWR meter also. The second directional coupler is connected to another detector probe. Let us call detector probe number 2, and this detector probe is properly terminated into a termination. Okay, and this second detector probe is connected to the device under test, DUT, whose different types of losses we want to measure. Okay, and finally this device under test is connected to the third detector probe, and this third detector probe is properly terminated into third termination. Okay, so this is a particular setup for measurement of different losses, different microwave losses. So this commonly used setup we are going to make use in order to measure different types of microwave losses. So this setup is constructed using a low power laboratory based microwave device. Okay, so we have a source over here. This is the first block. Second is isolator. Third block is a frequency meter. Fourth block is a variable attenuator. So fifth is a directional coupler. Sixth is also a directional coupler, and then here is the device under test whose different types of losses we want to measure is connected. Directional coupler 1, directional coupler 2, they are terminated with the detector probes, and the directional coupler 2 is placed with a match termination, while the device under test is again connected with a match termination. Right? So here how we are going to measure the different types of losses. Right? So here the procedure is, first of all, the matched load is connected to port 1. So here the port 1 is indicated over here. Okay, so port 1, so let us say this is port A. Let us call this condition as a port A. Okay, and let us call this condition as a port B. Okay, so situation A or situation B, you can call it as a, this is condition A and this is condition B. Right, and this is a condition C. So the connections, connection A is with the output device, connection B of the directional coupler 2 with the termination, and connection C is the connection of device under test with the termination. Okay, so what we do, first of all, see the setup procedure, how we measure the different types of losses. Okay, so what we do is, first we connect, I will write here, matched termination okay, we connect matched termination to port 2, connection A and connection C. Okay, so what we do is, over here initially we connect matched termination at connection A and connection B. So here I will show that this is initially connected to matched termination. Okay, in the step 1. Okay, and similarly connection C, probe detector 3 is already connected to match termination, right? And what we do is, in step number 1 we will place the output device at connection number B. So this output device, you can make use of a VSWR meter or you can make use of a CRO. So we connect match termination at A and at C with output device connected to connection B, right? This is the first step. So what we are doing in the first step, connection A we terminate with match termination, connection C is already terminated with match termination, and at connection B, that means at directional coupler 2, we will put the output device. This output device is a VSWR meter or it could be a CRO. Okay. Now what we do is we will measure the value in second step. We measure output. This output could be VSWR or voltage, depending upon what type of device you are using as output. So we measure the output at connection B. So what we do is, in second step, we measure the output at connection B. So this output will be either in the form of a VSWR or it will be directly a voltage if we are making use of a CRO or oscilloscope. Okay. Now this gives the ratio of power. Okay. This gives ratio reflected power to the incident power. So this ratio, when we measure the output at connection B, it will give the ratio of reflected power to the incident power, PR upon PI. Please remember. Okay. So then how the reflection loss is calculated? We know that reflection loss is calculated by subtracting 1. Okay. So in the third step, what we do is we calculate reflection loss. So how we calculate reflection loss? Simply subtract this ratio of power from 1. So this will provide us, in the denominator we have the incident power, right? In the denominator we have incident power. So if you subtract the ratio of power which we calculated in step number 2 with 1, we will get reflection loss. Okay. So what is the fourth step then? So we have got reflection loss in the step number 3. Okay. So next what we do is step number 4. Now what we do, we will not change any particular setup. Okay. So without disturbing this particular setup, okay, so what we do in the fourth step is, now the input attenuator is adjusted in order to get the signal equal at the directional coupler. Now what we do is, in step number 4, the match load or the termination is connected to port A and port B. Okay. So here now what we will do is, matched termination I will connect at port number A and B. Okay. So we connect matched termination, right? We connect matched termination at connection A and connection B. At connection A and B. So what we do now? Already at connection A we have the match termination. Now at connection B we will replace the output device, right? We will replace the output device with the match termination. Okay, so here I will draw Now this is connected to match termination, right, in this way. So connection A and connection B are connected to matched termination. Okay, and what we do is, now without disturbing this setup, we connected match termination at port number A and at port number B. And what we do is, we will connect the output device at connection C. So at connection C, and here I will write, and we connect output device at connection C. Now what we do is, port A and B, or connection A and B, we place match termination, and now we connect output device at connection number C. So at connection number C, this termination we will replace with output device now. Now this will become output device. Now this output device, either you can make use of CRO or you can make use of VSWR meter. Okay, and take the reading at connection number C. Okay, so measure output. This could be either VSWR or voltage at connection C. Okay, so if we measure the output at connection C in this particular setup without disturbing the any other part, so this particular measurement will give us the ratio of output power to the input power. So this gives, so here I will write below, this provides power ratio output power divided by input power. So this I will write output power divided by input power. Okay, so this is nothing but our insertion loss. Okay, so what is the insertion loss? If we recall this particular equation, we will get insertion loss in the fourth step. So this is nothing but insertion loss. Okay, so we already received reflection loss in step number 3. Now we have achieved insertion loss in step number 4. Then we can calculate attenuation loss. How we calculate attenuation loss? Attenuation loss is a simply subtraction. Then attenuation loss is given as insertion loss, we already know. So subtract reflection loss from this insertion loss. Reflection loss we achieved in step number 3, and insertion loss we achieved in step number 4. So we know the insertion loss, we know the reflection loss, simple subtraction, and calculate the attenuation loss. Okay, so this is a generalized setup of low cost loss measurement in the microwave signal. Okay, so the same setup can be used to measure the 3 different types of losses, particularly the insertion loss, the attenuation loss, and the reflection loss, right? So here the procedure is very simple. We need to make the arrangement of the setup in this particular way. We need 3 different detector probes, and we need 2 matched termination and 1 output device. That output device we may either use a VSWR circle, a VSWR meter, or a oscilloscope. So if you use VSWR meter, we will get the reading in terms of VSWR, or if I make use of a oscilloscope, we will get direct output in the form of a voltage. Okay, so initially what we do is, we connect matched termination at connection A and at connection C, and we connect the output device at connection B, and we measure the output at port number B or connection B. Now whatever the power ratio is being measured at terminal B, it will give me the ratio of reflected power to the incident power. Then from this I can calculate the reflection loss by subtracting 1 from it, and in the step number 3 I will get the reflection loss, right? Now in the next step what I will do is I will remove the matched termination the device from connection B, and the same device now I will connect at connection number C, and connection number B I will terminate with match condition. The other setup I will keep undisturbed. Okay, in the next step what I did is I will remove the device from connection B and I will connect the same device to connection C, and connection B is now terminated with match condition or match termination. And again I will measure the output at port number C or at connection C. Now this will give me the ratio of output power to the incident power, and this is nothing but the insertion loss. Okay, so in fourth number step I will get the insertion loss. Once I know the insertion loss and reflection loss, I will take the simple subtraction and I will calculate the attenuation loss. Okay, so with this procedural step and with this particular setup arrangement of microwave test bench, we can calculate all the different types of losses of the microwave for the given device under test. Please remember, the device under test is always remains in the circuit over here. Okay, so the different types of losses like insertion loss, right, attenuation loss and reflection loss, all these can be measured conveniently by placing the device under test in this particular setup. Okay, so this particular setup will provide us all the different types of microwave losses for which we will place this device under test. Okay, so this procedure explains us how the different types of microwave losses can be conveniently measured in the laboratory. Okay, and this completes the measurement of different types of microwave losses. In our next lecture we will again see some of the few other different types of parameters of the microwave and how they can be measured. So we'll stop over here and thank you very much.